Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. Today we will be discussing two different types of problems, non-isothermal diffusive mass transfer and then forced convective mass transfer. So, in the case of non-isothermal diffusive mass transfer, we are taking a problem where diffusion through a non-isothermal spherical film is taking place. Okay? Diffusion through hypothetical spherical stagnant gas film surrounding a droplet of liquid, that is the problem statement. So, consider the system as shown here in the picture. So, we have a droplet which is made up of the component A, and then gas film component B is there. The radius of droplet is R1, the radius of gas film surrounding this droplet is R2. Okay. The temperature of the droplet surface is T1, temperature at the gas film is function of ratio between these two radius power n. So, that is T2, which is given as T1 multiplied by R2 by R1 whole power n, right. So, now the component concentration XA is XA1 at R is equals to R1, and then component A concentration is XA2 at R is equals to R2. Now, if you have to consider the diffusion through non-isothermal situations, what you need to have information, you need to have a diffusivity as function of temperature. That information you should have, then only you can solve the problem. If that information is not available, you cannot solve the problem. You can solve the problem only for isothermal conditions. So, how the diffusivity is changing by change in temperature, that information should also be provided if you wanted to consider non-isothermal diffusive mass transfer problems. Okay. So, for that, a rough approximation of DAB, which varies as 3 by 2 power of the temperature, that is DAB divided by DAB comma 1 is equals to T by T1 whole power 3 by 2. So, the diffusivity, how is it changing with the temperature, is given by this expression. DAB comma 1 is nothing but diffusivity of a droplet A component in gas film B component at temperature T1, at fixed temperature T1, right. DAB is nothing but diffusivity at unknown temperature T. So, now the temperature is varying from T1 to T2, and then T2 is again function of T1 and then function of R1 and R2 as well as given this one. Okay. So, this problem we have to solve here. Okay. Then further applications, if you wanted to know here, such kind of applications in general, we have drying of droplets, where actually drying of droplets, when it is taking place, usually the size of the droplet decreases as the some of the components of droplet are evaporating. That is in general possible, but in this case what we are trying to take, we are taking the droplet radius is fixed. Later on, after a week or so, we are going to discuss similar kind of problem where evaporation of droplet or evaporation of column of liquid etc. would taking place. So, there we are going to take change in the position, interface position, that also we are going to take. So, that is in the later course, but since we are at the beginning of the mass transfer part, so then what we are taking the droplet radius is fixed even though it is evaporating, right. Applications we see drying of droplets, or sometimes what we have catalyst fillets are there. So, near the catalyst surfaces there would be some kind of diffusion of the components. Let us say on the catalyst surface some reaction is taking place. So, that product whatever is forming on the surface of the catalyst, that is passing through the gas film surrounding the catalyst surface and then reaching the bulk of the fluid. So, that is another kind of application. So, such kind of applications very common in chemical engineering. That is the reason we are taking this particular case to study under non-isothermal diffusive mass transfer. So, first what we do, the same problem we solve for the isothermal case first, then we go for the non-isothermal case, because it will be helpful to compare the results, how they are changing when you are incorporating non-isothermality of a diffusive mass transfer. Okay. So, that is the reason first we finish case 1 where we are taking isothermal case. So, we know that the combined flux NAR is equals to XA NAR plus NBR minus CDAB dXA by dr. Now, the mass transfer or diffusion is taking place in the radial direction. That is the reason the flux are designated with R, and then differentiation of concentration we are doing with respect to R. Okay. Now, if you do the steady state mass balance on a spherical shell, let us say if you have a droplet here. So, now you take a spherical shell, right. So, whose radius is R, and then the radius of the outer cell is R plus dr. So, that the thickness of the cell is dr, okay, and then this gas film, that is R2, is anyway it is there. So, between R1 to R2 values we are taking a spherical thin film of thickness dr, and for that one we are making the balance. So, when we do that one, so mass rate at R is equals to R is nothing but NAR multiplied by 2 pi R square, and then mass rate at R plus dr is nothing but NAR 2 pi R plus dr whole square, and should be equals to 0 because there is no reaction involved here in this case. Now, this one you simplify, you take dr tends to 0 and then apply the limiting conditions to get the differential form of this equation, then you get d by dr of R square NAR is equals to 0. Now, you can know the concentration profile if you know the NAR, but NAR you cannot know until and unless NBR is known. NAR expression you can find out from equation 1, that is fine, but that you can do only when NBR is known. But however, in this problem it is mentioned that non-diffusing stagnant gas film. So, that means B is not diffusing, only A is diffusing. So, that means if B is not diffusing, its flux would be 0, that is NBR is 0. So, now this equation 1 would become, when you take NBR is equals to 0, you get NAR is equals to minus C DAB divided by 1 minus XA dXA by dr. Now, here this you substitute in equation number 2, then you get d by dr of R square C DAB divided by 1 minus XA dXA by dr is equals to 0. Now, whatever the changes occur in this equation, that comes through this DAB and then C if non-isothermality is there. So, that we take as a case 2, but first case we are taking isothermal case. So, under isothermal conditions C and DAB both are constant. So, then if you take them as constant, then we have d by dr of R square by 1 minus XA dXA by dr is equals to 0. On one integrating once, we get R square by 1 minus XA dXA by dr is equals to C1. So, that is dXA by 1 minus XA is equals to C1 by R square dr. Now, once again if you integrate, you get ln 1 minus XA divided by minus 1. So, that is minus ln 1 minus XA is equals to integration of R power minus 2 is minus 1 by R. So, minus C1 by R plus another integration constant C2 you get it. Now, we have two boundary condition. At R is equals to R1, we have XA is equals to XA1. At R is equals to R2, XA is equals to XA2. So, when you apply these two boundary condition, you get these two expressions, simply replacing R is equals to R1 and then XA is equals to XA1, and R is equals to R2 and then XA is equals to XA2 in the second equation, in the first and second equations here respectively. Then what you do, subtract equation, you subtract the below equation from the above equation, then you get ln of 1 minus XA2 divided by 1 minus XA1 is equals to C1 multiplied by 1 by R2 minus 1 by R1, or C1 is equals to this one. This C1 you take and then substitute here in the first equation. So, you get C2, that is C2 is equals to minus ln 1 minus XA1 plus C1 by R1. So, 1 by R1 and then this is nothing but C1. So, now you have both C1 and C2 expressions you are having. So, those you substitute in equation number 4 to get the concentration profile. So, here you substituted C1 and this is C2. Then now you what you do, this particular component you take to the left hand side, so that you have minus ln 1 minus XA by 1 minus XA1 in the left hand side, and then right hand side minus ln 1 minus XA2 by 1 minus XA1 divided by 1 by R2 minus 1 by R1 is common if you take common. So, multiplied by 1 by R minus 1 by R1 you are having. right. So, this expression what we can write here, numerator also what I do, I write 1 by R1 minus 1 by R2, and then this one also I write 1 by R1 minus 1 by R, so that I have this expression, and then remaining term is as it is. So, concentration profile what you have, this is the expression you have given by equation number 5, right. Now, if you wanted to know the flux, what you have to do, you have to obtain the dxa by dr, because NAR expression we have dxa by dr, right. So, for that what we do, we take a concentration profile in this ln form, then we differentiate with respect to R both sides. So, first left hand side, if you differentiate with R, you get 1 by 1 minus xa by 1 minus xa1 multiplied by 1 by 1 minus xa1, and then minus dxa by dr. You are getting right hand side, this and these are constant. So, that and then remaining term, if you do the differentiation, you get this is also constant. So, 0 minus of minus 1 by r square as differentiation. So, then you have this one plus 1 by r square in the right hand side, and then left hand side this is what you are having, right. So, this 1 minus xa1, this 1 minus xa1 you can cancel out, and then this 1 minus xa you can take it to the right hand side, or you keep it here itself, there is no issue, right. So, if you take to the right hand side, so this is what you are having. Now, but this dxa by dr we need at r is equals to r1. Flux we wanted to calculate at r is equals to r1, because from that surface only, from that position only droplet is evaporating. Surface, evaporation is taking place from the droplet surface, which is designated as at r is equals to r1. So, that is the reason this flux we have to calculate at r is equals to r1. So, this dxa by dr also we should calculate at r is equals to r1. So, when you do at r is equals to r1, xa is nothing but xa1, and then r is nothing but r1. So, rest other terms are as it is. So, this is what we get, minus dxa by dr at r is equals to r1. Now, flux NAR at r is equals to r1 is nothing but minus C dAB divided by 1 minus xa1 dxa by dr at r is equals to r1. xa1 because we are calculating this one flux at r is equals to r1. So, that is C dAB by 1 minus xa1, and then minus dxa by dr is this one. So, 1 minus xa1, 1 minus xa1 cancelled out, C dAB ln of this term, and then 1 by r1 square, and then this term. This is the flux. Now, if you wanted to know the rate of mass transfer in terms of moles per time, that is WA is molar flow of A at the surface of spherical droplet of radius r1. So, what you have to do, this flux whatever is there, that you have to multiply by surface area through which the mass transfer is taking place. Surface area of the droplet, that is at r1 location, that is 4 pi r1 square is the surface area of the droplet. So, flux if you multiply by this surface area, you get the mass transfer rate in moles per seconds. That expression is given this one. So, now 4 pi r1 square. So, this r1 square is cancelled out. So, the remaining term is this one. So, this is the isothermal case. Now, we take non-isothermal case of the same problem. So, this non-isothermal case up to derivation of NAR is equals to minus C dAB by 1 minus xa dxa by dr, up to that point it is quite same, because till that point temperature issue has not come into the equations or any of the balances. Okay. So, combined flux is this one. So, steady state balance is the same like isothermal case. Then by applying the limiting conditions, you get the differential form of this equation, this balance equation given by equation number 2. But NBR is 0 because stagnant non-isothermal stagnant gas film. So, gas film is not diffusing, non-diffusing stagnant gas film, that is the statement is given. So, B is not diffusing, gas film is of component B. So, NBR is 0. So, that again you substitute in equation number 1, you get NAR is equals to this one. So this one you substitute in equation number 2, so then this equation you get. So now this equation you have to solve for non-isothermal conditions. Till now the non-isothermality has not brought into the picture. There is no term which required to consider this non-isothermality here. So till this point it is solution is same as case 1. So from here it will change. So now this relation is given, dAB by dAB comma 1 is nothing but T by T1 power 3 by 2, and then this T by T1 is given by R by R1 power n. So now what we can write, dAB divided by dAB comma 1 is equals to R by R1 whole power 3 n by 2. You may be thinking that in place of dAB we can, why can't we write dAB comma 1 multiplied by T by T1 whole power 3 by 2. So that way we can write and then do the differentiation, but the T is related to the R. T is related to the R that is given in the statement. So the T is also function of R. So then we have the differentiations and then integration subsequently in the calculation. So until and unless this T function of R, if you don't include, so the solution will not be reliable, because T function of R, that statement is given in the problem, that should also be incorporated. Had that not been given, so then we should have taken only dAB is equals to dAB comma 1 multiplied by T by T1 power 3 by 2, that's it. So but now T by T1 is given by this expression in the problem statement, so that information should also be brought into the picture. Further, C we can write as P by RT, and then T is nothing but T1 R by R1 power n. Right. So now in this equation, equation number 3, in place of C, in place of D, we have to use these two expressions. Okay. That if you do, d by dr of R square, C is nothing but P by RT1 R by R1 power n, R by R1 power 3 n by 2, dAB comma 1, that is nothing but dAB, and then 1 by XA and then dXA by dr is equals to 0. So that you rearrange. Now this R square is as it is, P dAB comma 1 by RT1 are constant now, 1 by 1 minus XA as it is, dXA by dr is as it is. So remaining terms, whatever this R by R1 whole power 3n by 2 and then R divided by R by R1 power n, we can write R by R1 power n by 2. Right. So that is what this additional thing. Now you can integrate. So then left hand side differentiation will go off, and then we have a C1 constant in the right hand side. So this one R square and then R power n by 2 divided by R1 power n by 2 we are separating out, so that we can combine this R power n by 2 and then R power 2 as one term, so that it will be useful in integration subsequently. So that R power n by 2 plus 2 is there, that we are taking to the right hand side. Even this dr also we are taking to the right hand side. So we are getting dr by R power n by 2 plus 2 C1 in the right hand side, all other terms in the left hand side. So in the left hand side, except dXA by 1 minus XA, everything is constant. Right. So the same equation is written here. So what we do for simplicity, we take this expression which is a constant, we represent by lambda, so that lambda also we take into the right hand side, so that we can write C1 by lambda as a one constant, and then remaining terms are as it is. Okay. Now if you integrate this equation again, you get left hand side ln 1 minus XA by minus 1, so that is minus ln 1 minus XA, C1 by lambda is constant, and then integration of R power minus n by 2 minus 2 is nothing but this one plus C2 constant. So when you simplify, this is what you have this equation. Right. Now we have two boundary conditions. At R is equals to R1, XA is equals to XA1. So we have this equation. In place of XA we are writing XA1, in place of R we are writing R1. Other boundary condition, at R is equals to R2, XA is equals to XA2. So same thing here, in place of XA we are writing XA2, in place of R we are writing R2, rest all other terms are same. So now this equation minus this equation, if you do, you get an expression for C1, because C2 minus C2 is 0. So, this is what you get, and then from here C1 you get this expression. Now, this C1 if you substitute in this equation you get C2, this is BC1, that is at R is equals to R1, XA is equals to XA1, whatever we have written, that equation is this one, right. So, now here C2 is equals to minus ln1 minus XA1 minus C1 by lambda minus 1 by lambda, and then this is all C1 from 7a, equation number 7a. So, now we have C1, C2 here. C2 what we can do, we can simplify slightly, this lambda, this 1 plus n by 2, this 1 plus n by 2 cancelled out. So, remaining terms are this, and then this term is as it is. So, 7b C2, 7a C1. So, this constant C1 C2 if you substitute in the equation 6, that is minus ln 1 minus xa is equals to C1 by lambda r power minus n by 2 plus 1 divided by minus n by 2 plus 1 plus C2, right. So, now C1 C2 you substitute 1 by lambda, this is C1, this entire thing is C2. Now, what we do, this this ln 1 minus xa1 term, that we take to the left hand side, so that we can have left hand side minus ln 1 minus xa by 1 minus xa1, and then remaining terms, the first term here lambda you can cancel out, and 1 plus n by 2, 1 plus n by 2 also you can cancel out. So, the remaining terms, from the remaining two terms you can take ln 1 minus xa1 divided by 1 minus xa2 common, then we have r1 power minus 1 plus n by 2 minus r power minus 1 plus n by 2 divided by r1 power minus 1 by 1 plus n by 2 minus r2 power minus 1 plus n by 2. So, then all of these r's are having power minus, so then we can write a reciprocal of them. So, when you write, so then this is what you are having multiplied by ln 1 minus xa1 divided by 1 minus xa2. So, under the non-isothermal conditions, the concentration profile for this spherical gas film problem, diffusion of droplet to a spherical gas film is provided by this expression, right. Now, if you wanted to know the flux, what you have to do, you have to find out dxa by dr. So, for that what we do, this equation whatever is there, that we differentiate with respect to r. So, left hand side what we will be having, minus 1 by 1 minus xa by 1 minus xa1 multiplied by 1 by 1 minus xa1 minus dxa by dr you get in the left hand side. Right hand side, this is constant, this is constant, this is constant, this is constant. So, only this one we have to differentiate. So, in the numerator we will be having 0 minus 1 minus n by 2 r power minus 1 minus n by 2 minus 1. This is what we have. Rest all other terms are constants in the right hand side. So, then we have right hand side this particular term as written here. So, 1 by 1 minus xa by 1 minus xa1 I can write 1 minus xa1 by 1 minus xa, and then remaining two terms as it is. Right hand side we have this term is constant, and then denominator is constant, numerator differentiation you get this expression, right. So, this if you write dxa by dr one side, and then 1 by 1 minus xa one side, rest all other terms to the other side if you take. So, here this 1 minus xa1, 1 minus xa1 is cancelled out. So, the remaining terms are as it is, right hand side term, this is what we got, okay. So, now we need the flux at the droplet surface which is evaporating. So, at r is equals to r1 we have to get this expression. So, at r is equals to r1, xa is equals to xa1. So, whatever 1 by 1 minus xa1 in the left hand side, that also we brought to the right hand side, and then in this expression whatever this r power minus 2 plus n by 2 is there, that I am writing 1 by r power 2 plus n by 2, and then r we are replacing by r1. So now this flux NAR at r is equals to r1 is nothing but minus C dAB divided by 1 minus XA1 dXA by dr at r is equals to r1. So this part is as it is. dXA by dr is given by this expression. Just previous slide we got it. Okay, so this 1 minus XA1, this 1 minus XA1 is cancelled out, and now this C is nothing but P by RT, and then dAB is nothing but dAB comma 1 r by r1 whole power 3n by 2. So those things we are writing, and then T is nothing but T1 multiplied by r r1 power n, right. So now this we are actually evaluating at r is equals to r1. So r by r1 by r1 is 1. Similarly, this also we are evaluating at r is equals to r1. So r by r1 is 1. So whatever the power doesn't matter, 1 power anything is 1, right. So now here, so this is what we get. So finally the flux is given by this expression, P dAB comma 1 by RT1 multiplied by this particular term, right. Now if you want to know the mass transfer rate in moles per second here, so whatever NAR at r is equals to r1 is there, that we have to multiply it by surface area of the droplet, that is 4 pi r1 square, because from the droplet surface the transfer of the mass is taking place, right. So NAR at r is equals to r1 is nothing but this one. So now this r1 square can be cancelled out, so then we have only r power n by 2 here. So that r is also at r is equals to r1. Okay, so remaining all terms are same. So now this equation, if you write P by r T1 r by r power n as C, and then dAB is equals to dAB comma 1 r by r1 power 3n by 2 if you write, and then you take n is equals to 0, then this expression will reduce to the solution of so called isothermal case. You can cross check it is, right. So this is about the non-isothermal diffusive mass transfer. Now we take another case where we are considering forced convective mass transfer. Okay, for this situation of forced convective mass transfer, we are considering diffusion into a falling liquid film. There is a liquid film, so that is falling with certain velocity, so there is a velocity distribution. That velocity distribution is affecting the diffusive mass transfer. How it is affecting, that we have to find out, right. So it is also possible that diffusion is taking place into the liquid film, so then liquid composition may change and then viscosity may change, that is also possible. So can we handle that situation? If not, how we have to make approximation, simplification, and all those things we have to see. So this is an example of forced convective mass transfer as explained, where viscous flow and diffusion are under such condition that velocity field can be considered as unaffected by the diffusion. That is, momentum transfer is not affected by the mass transfer, but mass transfer is affected by the momentum transfer. Okay. So this mass transfer is not affecting the momentum transfer, but momentum transfer is affecting the mass transfer. So this is the situation. This can be possible when diffusion is only taking place slightly. If it is taking place only slightly, then what happens, the composition of liquid composition does not change much. So liquid viscosity does not change, so then obviously its velocity distribution will not be affected, because here it is a thin film, it is a thin film only. Okay. So that is considering that absorption of gas A in a laminar falling film of liquid B. So B is liquid component, A is the gas film which is diffusing. So this A gas is diffusing into B liquid. Other assumptions, material A is only slightly soluble in B, so that viscosity of liquid is unaffected. Then only we can say that mass transfer is not affecting the momentum transfer. diffusion takes place so slowly in liquid film that A will not penetrate very far into the film. So, into the film, the transfer is taking place, and then that is penetration distance is small in comparison with film thickness. Okay. So, now pictorial, if you see, three-dimensional projection is shown here. So, the horizontal axis is x, vertical axis is z, right. So, the height of the column is L, width of this column is W, through which along which the material is flowing down. So, there is this material whatever is there, that B liquid is there. So, that is falling like a film here, right. And now into this film the diffusion of component A is, gas component A is taking place. So, how do you visualize this location? So, what you have to see, this Z is equals to 0 is this top location of the column, Z is equals to L is the bottom location of the column. Now, left hand side x is equals to 0 we are taking, right hand side x is equals to delta we are taking. If it is a in a 2D diagram it is shown here. If you visualize in 3D diagram, x is equals to delta is nothing but your screen on which you are studying, right. Or if you are if we are discussing this problem on a board, x is equals to delta is a board location, and then from the top of the board the material is falling, right. X is equals to 0 is location is the outermost layer of the liquid which is exposed to the gas, surrounding gas. So, x is equals to 0 is the surrounding gas. The same thing if you visualize like this. So, this is the surface, let us say this palm is a surface. Now, from the top the liquid is flowing down like a film, right. From the top liquid is flowing down like this. So, x is equals to delta location is the palm surface. Let us say x is equals to 0 is the film thickness is delta. So, that is coming here. So, the tip of the pen whatever is there. So, that is x is equals to 0. Right. So, now this pen entire thing whatever is there, that is the gas film, and then that area, let us say, you can say. So, x is equals to 0 here, the gas is coming and then diffusing into the liquid film like this, right. So, that is what the problem. So, when these gas film molecules are diffusing into the liquid film, how the concentration profile of this gas film, whatever the gas component A is there, so that we have to find out. So, when these molecules of gas A are diffusing into the liquid film B, so how the concentration of this gas A is changing in the thickness of this film, that is from x is equals to 0 to x is equals to delta, that you have to find out, right. So, that is one thing. Other thing is that it is mentioned in the problem that this is penetrating only to a smaller distance. So, only that, let us say from this is x is equals to 0, it is penetrating only to small distance only. After that it is not able to penetrate completely to reach the wall surface. That is the limitation is given. So, why that limitation is given? When it is only slightly soluble or penetrate to small penetration thickness, you can say that viscosity of this film, liquid film, is not affected. So, velocity the film thickness, velocity distribution within the film will not be affected. So, this understanding is important. Once you have this understanding, problem solving is very simple. So, now we see the boundary conditions also here. These all these details are given in the subsequent slides also, but from picture if you understand it will be easy. So, Z is equals to 0 is the location at the top where the pure liquid is there. Pure liquid is there, and then that is falling as a film. So, concentration of A should be 0 because pure liquid B is there. If the liquid B is pure, so then there is no A, that is what it means by. And then at other location Z is equals to L, what is Ca? That is not given to us. So, let us not worry about it, we will think of it. And then x is equals to 0, what we have? That is the free surface, that is of the liquid film, free surface of the liquid film which is exposed to the gas, that is the very first layer of the liquid film at which gas is coming and then interacting and then further penetrating into the film. So, that should be its initial concentration Ca naught which is usually taken as the solubility of that particular component A and B. So, we are taking Ca naught, and x is equals to delta. What we have? It has been mentioned that this component is penetrating to only smaller distance only. A is able to penetrate into the smaller distance only. That's the reason its concentration is varying. Variations in concentration is shown in pictorially only for small distance. After that, it is almost remaining same. That means we can say dou Ca by dou x is 0. Right. So now from the this penetration distance, let us say if I call it some alpha, let us say. So penetration distance alpha is very smaller than the film thickness delta. So whatever the molecules at this surface are there, at the free surface, they can never reach to this wall of the plane, which is at x is equals to delta. So when the penetration distance alpha is very small compared to the delta, what we can say, from the molecules of the gas film viewpoint, this delta location is far away from their position, so they cannot go there. It is so far away that it can say that x is equals to infinity from the molecules, gas molecules viewpoint of view. So at x is equals to infinity, the molecules are not able to come up to this location. They are penetrating only up to smaller distance. So after that, presence of Ca is 0. It is not there. So Ca should be 0. So the conversion of this boundary condition like this is very essential in solving this problem. Otherwise, we are not able to solve this problem. It is similar like previous heat transfer case where the flow through non-isothermal flow through cylindrical pipe were taking place, where T was taken as function of both R and Z. So similar kind of situation here also. Here concentration is function of both X and Z. We cannot say Ca is function of only X, it is function of Z also. So we need to know two boundary conditions in the Z direction, two boundary condition in the X direction. So in the Z direction, we have only one boundary condition we can specify, other boundary condition at the bottom we cannot specify. We cannot even say dou Ca by dou Z also 0. We cannot say that one physically. Other two boundary condition in this direction, so these are the things, but this boundary condition has been simplified like this. From the molecules of gas molecules A viewpoint, we can say that x is equals to infinity, Ca is equals to 0, which is same as x is equals to delta, dou Ca at x is equals to delta, dou Ca by dou x is 0, because the penetration distance or penetration depth whatever is there, that is very small compared to the film thickness. Actually film itself is very thin. It's a few mm thickness film usually. Most of the polymer industries we have this kind of problems. Remember in one of the course momentum transfer, we have seen that we have an inclined plate and then the fluid is flowing down. So then we found the velocity profile, etc. So now here the same situation is there, but only thing that we have taken the vertical plate, and then in addition to the momentum transfer, there is a mass transfer is also occurring. So it's a combined mass transfer and momentum transfer. That is what we are calling forced convective mass transfer, because the flow whatever the velocity distribution is there, that is affecting the mass transfer also. Now this velocity distribution here we see at x is equals to 0 is the outermost layer of the fluid which is having the maximum velocity, and x is equals to delta is nothing but the surface of the plane on which the material is flowing. So because of the no slip condition, the velocity would be 0, Vz would be 0 here, and then Vz would be maximum here at x is equals to 0. And then between these two locations the velocity profile changes like this, which is function of x. So that also we have to find out. Okay. So this understanding is very much essential. So after that everything is mathematical only. Since here the velocity also needed to be find out. So first what we do, we simplify the conservation of mass and momentum in order to get the velocity profile. So, continuity equation in Cartesian coordinates is given here. Only Vz is there, and then it is not function of z, it is function of x only. So, this is 0, Vy, Vx are anyway 0. So, then continuity is satisfied. X component of equation of motion is given here. So, here Vx steady state, so this term is 0, Vx is 0, Vy is 0, Vx is 0, right, Vx is 0. So, all these 3 terms are 0, and then gravity we are taking only in the z direction as per the schematic. So, Gx is 0. So, dou p by dou x is 0. Similarly, y component of equation of motion is given here. Steady state, this term is 0, Vx is 0, Vy is 0, Vy is 0, Vy is 0. So, all these 3 terms are 0. Gravity is only in the z direction. So, this term is also 0. So, we have dou p by dou y is equals to 0. Then z component of equation of motion is given here. Steady state, this term is 0, Vx is 0, Vy is 0, Vz is existing, it is function of x, but it is not function of z. It is function of x only, it is not function of z. So, this term is also 0. And then the film, whatever the film that is falling, it is falling because of the gravity only, or compared to the gravity, pressure forces are 0 here, because the film is falling because of the gravity in the z direction, right. So, Vz is function of x, so this term would be there, but Vz is not function of y and z, so these 2 terms are 0. So, then we get mu dou square Vz by dou x square is equals to minus rho Gz, and Gz is nothing but G. So, you take the mu also to the right hand side, then integrate first time. So, minus rho G by mu x plus C1, left hand side dou Vz by dou x. If you integrate again, Vz is equals to minus rho G mu x square by 2 plus C1x plus C2. Then BC set x is equals to 0, Vz is maximum. So, dou Vz by dou x is 0. If dou Vz by dou x is 0 at x is equals to 0, from this part of the equation we get C1 is equals to 0, right. And then at x is equals to delta, Vz is equals to 0. So, then Vz is equal, if Vz from this part of the equation you get V0 is equals to minus rho G del square by 2 mu plus C1 delta plus C2. C1 is 0. So, C2 is equals to rho G delta square by 2 mu you get. So, this C2 you substitute here in this equation, C1 is anyway 0. So, this term is gone. So, then you have this thing, and then out of these 2, if you take rho G delta square by 2 mu common, you get 1 minus x square by delta square. And then maximum velocity, where are we having? At x is equals to 0, Vz is maximum. So, Vz is equals to Vz max is equals to rho G delta square by 2 mu, because x is 0 here. So, this same equation we can write Vz is equals to Vz max multiplied by 1 minus x square by delta square we can write. So, that is given here. Now, velocity distribution you got it. Now, what we have to do? You have to find out the concentration profile. For species A, this species transfer equation is this one, like heat transfer equation we have, like momentum transfer equation we have. This species transfer equation is provided by this one. We can find out any books, we can derive this one also. So, this steady state, this term is 0, Vx is not existing, Vy is not existing, Vz is existing, and then C is concentration of A, which is function of Z, and then X also. So, this you cannot cancel out. Now, DAB, this CA is function of X, so this term should be there, but it is not function of Y, so it is 0. C is function of Z also, but what we have, the convection in Z direction is much higher compared to the diffusion in Z direction. So, pictorially what we have, the diffusion is taking place in the X direction. So, diffusion is dominating in the X direction, convection, the flow is taking place in the Z direction. So, convection terms are dominating in the Z direction, diffusive terms are dominating in the X direction. So, diffusive terms whatever in the z direction is there, so that would be small compared to either of these two terms, that is diffusion in x direction and then convection in z direction. So, accordingly this term can be cancelled out. There is no reaction finally. So, what we have? We have Vz dou Ca by dou z is equals to dAb dou square Ca by dou x square. This Vz is what? Vz max 1 minus x by delta whole square dou Ca by dou z is equals to dAb dou square Ca by dou x square. Fine. Now, boundary conditions we have already seen at z is equals to 0 at the top of the column pure liquid B is there. So, gas A concentration is 0. It indicates that the film consists of pure B at top, that is z is equals to 0 location, and x is equals to 0, that is the free surface, indicates that the liquid gas interface, and then concentration of A is determined by the solubility of A in B, that is Ca naught, maximum concentration of A that is possible at the interface, that is Ca naught, right. And then at x is equals to delta dou Ca by dou x is equals to 0, this is also we have seen, that indicates that A cannot diffuse through the solid wall. Now, this whatever the equation we had, 1 minus x square by delta square, of course Vz max dou Ca by dou z is equals to dAb dou square Ca by dou x square. So, this equation if you wanted to solve, you have to have certain limitations. Like in a heat transfer case, non-isothermal flow in pipe, what we have taken a asymptotic approximation. So, like that some kind of limitations is required. So, then in this case one can get only a limiting expression for Ca valid for short contact time, that is when L by Vz max is very small, then only one can get the solution easily, right. So, why short contact time? Because within that small time only Ca the A is able to penetrate to smaller distance into the liquid film, only a smaller distance, that is the reason. So, accordingly substance A has penetrated only a short distance into the film. So, this is the given statements, both of them are now interconnected, right. So, A has impression that film is moving throughout with a constant velocity equal to Vz. Now, here also Vz max, because the A knows that it is only able to penetrate. Now, this is the entire film, but the gas molecules are here. So, the molecules are penetrating only to small distance into the liquid film, that gas molecules are in an impression that the film is moving with a constant velocity of maximum velocity that is possible at the gas liquid interface, because it is penetrating only to a smaller distance. It is these gas molecules are not aware of the surface of the wall, which they assume that the surface of the wall is at infinite distance from their location of x is equals to 0. This is with respect to the gas molecules viewpoint, especially they are penetrating to a small distance. So, A does not penetrate very far, that it does not sense presence of solid wall at x is equals to delta. Therefore, if film were of infinite thickness moving with velocity Vz max, then the diffusing material would not sense the difference in the velocity, and then this physical argument suggests that one can get a very approximate result if the equation 3 this whatever and then boundary condition whatever you mentioned is approximated like this. So, this equation now x by delta is almost like 0. X by delta, x is the distance from the view molecules point from the gas molecules point of view, x is equals to 0 to certain x value is there, that is the penetration depth, right, from x is equals to 0 to some x location, which is this difference is, let us say, alpha penetration depth we are calling. So, this alpha is very small compared to the delta. So, x by delta is almost like 0. So, then this we can take off. So, that left hand side we have Vz max dou Ca by dou z is equals to dAb dou square Ca by dou x square. This is about the simplified governing equations after couple of assumptions, which are physically reliable of course. Then boundary conditions, at z is equals to 0, Ca is equals to 0, that will be as it is. At x is equals to 0, Ca is equals to Ca naught, that would also be as it is. But at x is equals to delta location is almost like infinite location, very far for the gas molecules, because they are penetrating only smaller distance into the film and they are not able to sense the presence of wall. So, they are thinking that those molecules are thinking that x is equals to delta is virtually x is equals to infinity, and they cannot go up to that location. If they cannot go up to that location, their concentration at that location is 0, Ca is equals to 0. So, this also pictorially we have explained. So, now here still the problem is very difficult to solve, because now Ca is function of both z and x, right. So, we cannot say that one side is independent of the other side, like we say, like we did in order to get the shear stress expressions etc. here. So, that is not possible. So, for that what we do? We do combined variable approach. For that we are taking dimensionless parameters Ca by Ca naught as Ca prime, and then this one what you do, you can write from here. So, this dimensionless parameter, which is having the both x and z together, that is a combined variable. We can call this eta, we can call combined variable now. Okay. So, how you get this expression particularly? Let us say from this equation what we can write, Vz max divided by z is equals to dAb divided by x square. So, if I write this one, x square is equals to dAb z by Vz max. So, if I take a square root of both sides, so x by square root of dAb z Vz max, this kind of form we can have. This 4 we are getting because of the experience of solving the problem, we can have this constant. So, this we are writing as eta. This is how we can decide how this combined variable should be defined. This is how we can do it. Okay. So, now this equation Vz max, in place of dou Ca by dou z, I can write Ca naught dou Ca prime by dou z, and then right hand side in place of dou square Ca by dou x square, I can write Ca naught dou square Ca prime divided by dou x square. So, the Ca naught is cancelled out, and then this is what we are having. Now, this equation this equation, now here it is function of z and then x both. So, now we convert this as a function of one combined variable eta using this definition of a dimensionless parameter. So, how we do? So, let us say dou Ca prime by dou z is equals to dou Ca prime by dou eta multiplied by d eta by dz. Since now this Ca prime we are writing as a function of only one variable, in place of dou I am writing d directly. Okay. So, now this expression from here, what you get, d eta by dz is nothing but x divided by square root of 4 dAb divided by Vz max, and then d by dz of z power minus 1 by 2. So, that is minus 1 by 2 z power minus 3 by 2. So, z power minus 3 by 2, what I am writing, minus 1 by 2, and then 1 by z square root of z I am writing, and this square root of z I am combining with this remaining terms. So, that I can write 4 dAb z by Vz max, and then 1 by 2z minus 1 by 2z as it is, this dCa prime by d eta as it is. So, now this again, what is this? This is nothing but our eta as per the definition of combined variable. So, this is what we are having. Similarly, dou Ca prime by dou x, if you do, that is dou Ca prime by dou eta d eta by dx. D eta by dx is nothing but 1 by square root of 4 dAB Z by Vz max, right. So, now when you are doing the differentiation of eta with respect to x, z has to be treated as constant. Similarly, when you are doing the differentiation of eta with respect to z, x has to be treated as constant, like in partial derivatives. Then this is what we have. So, once again, if you differentiate with respect to x, this equation, you get this form. So, now we have dou Ca prime by dou z and then dou square Ca prime by dou x square from equation number 12 and 14. These we substitute here in this equation. So, that is dou Ca prime by dou z and dou square Ca prime by dou x square we are substituting in this equation. Then what we have? Vz max, we can do this one. Dou Ca prime by dou z is minus eta by 2z dCa prime by d eta is equals to dAB, and then this part is 1 by 4 dAB Z by Vz max d square Ca prime by d eta square. So, now this dAB is cancelled out, left hand side 1 by z, right hand side 1 by z cancelled out, left hand side Vz max, right hand side Vz max cancelled out. So, what we have? We have minus eta by 2 dCa prime by d eta, and then this 2 also we can take off because 2 1 ja 2 2 ja. So, we have 1 by 2 d square Ca prime by d eta square. So, that is this 2 you take to the left hand side and then you add them together by taking d square Ca prime by d eta square plus 2 eta dCa prime by d eta is equals to 0. So, now this equation, which is function of both x and z, has been converted into the function of one single variable eta, right. So, this is what we have. So, coming to the boundary conditions, at x is equals to 0, what we have? Ca is equals to Ca naught. If x is equals to 0, that means from this definition of combined variable, eta is 0, and then eta is 0, that means Ca by Ca naught is equals to 1. Ca by Ca naught is nothing but Ca prime, so that is equals to 1. And then other equation, at x is equals to infinity, that is Ca is equals to 0, that we understand. So, if x is equals to infinity, that means eta is equals to infinity, and then if Ca is 0, Ca prime is also 0, because Ca prime is nothing but Ca by Ca naught. So, these are the two boundary conditions in terms of eta, which are getting from these two expressions. So, now this equation number 15 we have to solve using these boundary condition given equation number 16 and 17. So, let us say you take dCa prime by d eta, dCa prime by d eta is equals to psi, then we have d psi by d eta plus 2 eta psi is equals to 0, right. So, the same equation you have written like this by taking these two to the right hand side, then you are taking eta terms, psi terms separately, two different sides. So, then integrating, so you get this one. Now, after removing the logarithmic, you get this one. Now, psi is nothing but dCa prime by d eta, that is C1 exponential of minus eta square. So, dCa prime is equals to C1 exponential of minus eta square d eta, that is Ca prime is equals to C1 integral of this one plus C2, we are writing in it in terms of dummy variable, same like that, and then integration from 0 to eta, right. So, this is what we have. We are not evaluating these constants directly, but we apply and then see what we get. So, in the first bound, this is the equation. First boundary condition is that eta is equals to 0, Ca prime is equals to 1. So, 1 is equals to C1 integral 0 to 0 exponential of minus eta bar square d eta bar plus C2. Integral 0 to 0 is there, whatever the integration, when you substitute both limits are same. So, then that will be 0. So, then C2 is equals to 1. right. Other one is at eta is equals to infinity, Ca prime is equals to 0. So, that is C1 integral 0 to infinity exponential of minus eta bar square d eta bar plus C2. C2 is nothing but 1, it is given. So, C1 you can get minus C2 by this one, and then C2 is nothing but 1. So, this is C1, this is C2. If you substitute these two in this equation, you get the expression for Ca prime as this one. This we can write Ca prime is equals to 1 minus of this one, and this is nothing but defined as error function of eta. This is by the definition of error functions, which is given by this expression. Okay. Then the Ca prime is nothing but Ca by Ca naught 1 minus 2 by square root of pi integral 0 to eta is nothing but this one exponential of minus eta bar square d eta bar is equals to 1 minus error function of eta. So, this whatever is there, so this entire thing we can write is error function of eta, that is error function of x by square root of 4 dAbz by Vz max. 1 minus error function of x is nothing but complementary error function of x. So, that is given is ERFC x by this one. Okay. So, that is the concentration profile. If you wanted to know the flux, you have to find out the dou Ca by dou x. So, Ca by Ca naught is this one. So, dou Ca by dou naught is nothing but this one, and then from the definitions d by dx of error function of u is equals to this one. That if you apply, you get for our case this one. Okay. Now, here you substitute whatever d eta by dx is nothing but 1 by square root of 4 dAbz by Vz max, right. So, dCA by dx at x is equals to 0, that means here if you substitute x is equals to 0, what happens? Eta is 0. If x is equals to 0, that means eta is 0. So, exponential of 0 is 1. So, the remaining terms would be there. The square root of 4 is nothing but 2. So, that is cancelled out, right, and then this pi also we are taking into the square root of term. So, minus Ca naught square root of Vz max by dAb by Vz max by pi dAbz, that is what we get. So, this Nax at x is equals to 0 is nothing but minus dAb dou Ca by dou x at x is equals to 0. So, that dou Ca by dou x at x is equals to 0 is nothing but minus of this one. So, plus of this one we are having, and then multiplied by dAb was there. So, dAb by square root of dAb we have square root of dAb. So, that is square root of dAb Vz max by pi z we are having. Now, mass rate if you wanted to find out, you have to multiply, you have to get Wa is equals to integral 0 to W 0 to L Nax x is equals to 0 dz dy. So, that is W Ca naught square root of dAb Vz max by pi integral of 0 to L 1 by square root of z dz, because Nax at x is equals to 0 is nothing but this one. Now, integration of dz by square root of z, if you do, you get simplified expression this one here after substituting limits here. So, now what we understand, Wa is proportional to the square root of diffusivity, and then Wa is inversely proportional to the square root of L by Vz max. L by Vz max is nothing but the time, contact time, inversely proportional to the contact time, but directly proportional to the diffusivity. So, this is how we have to solve the convective mass transfer problems. The references for these lectures are provided here. Thank you.